Welcome to the fourth lecture on the category of vector spaces titled Subspaces. Let's review our previous lectures. Let's fix a field K throughout this presentation. A vector space V plus dot is an algebraic structure with an addition and a scalar multiplication subject to certain relations. A linear map phi from V to W between two vector spaces V and W is a function from V and W such that for all two vectors x and y in V and for all scalar lambda, phi of lambda x plus y equals to lambda phi of x plus phi of y. Linear maps are the morphisms between vector spaces in the sense that the identity of any vector space is linear and the composition of it in two linear maps is again linear. Now, for the pointwise addition and scalar multiplication, the set of functions from any non-empty set D to a fixed vector space V is a vector space in its own right. And in particular, this implies that k to the n is a vector space for all natural numbers. Now, there are many vector spaces which in fact lie inside the examples that we have seen in the previous lectures of standard vector spaces, so that k to the n, the space of function from a given set to a vector space, or even the product of arbitrary many vector spaces. Those spaces that lie inside a vector space will be called subspaces and are the topic of today's lecture. A subspace W of a vector space V plus dot over a field K is a subset W of V such that the neutral element of V, the zero vector, belongs to W. For all scalar lambda and for all vector x in W, lambda times x is again in W. And for all two vectors x and y in W, x plus y also belong to W. In other words, a subspace is a subset of a vector space which contains the zero element and is closed under both addition and scalar multiplication. We are going to characterize subspaces of a vector space in a manner akin to our characterization of linear maps. A subset W of a vector space V over a field K is a subspace of V if and only if W is not empty, and for any scalar lambda and any two vectors x and y in W, lambda x plus y is again in W. Let's prove the theorem. First, let W be indeed a subspace of V. Let's prove that it satisfies the blue box statement of the theorem. So, first we note that since 0 by assumption is in W, as the first property of the definition, which is now highlighted, shows, we must have that W is not empty. Second of all, if we pick two vectors x and y in W and a scalar lambda, then lambda times x is in W by the second highlighted property right now in the definition of a subspace. And now lambda x and y are together in W, therefore by the third property in our definition, which I have now highlighted, lambda x plus y is in W. Therefore, a subspace does indeed satisfy the condition of the theorem. Let's prove the converse. Let W be some non-empty subset of V such that, for any x and y in W and any scalar lambda, lambda x plus y again belongs to W. I wish to prove that W is a subspace, so first I'm going to prove that 0 indeed belongs to W. To do so, I need to write 0 as a vector of the form lambda x plus y with x and y in W and lambda some scalar. Using the work in our previous lectures, we realize that 0 is indeed equal to minus 1 times x plus x for any x, and since W is not empty, I can pick an x in W and have written 0 in the right form to conclude that 0 does belong to W indeed. Second of all, I'm going to prove that W is closed for the addition. Let x and y be two vectors in W. I'm going to rewrite x plus y again in a form compatible with the conditions of our theorem. But it is easy because we know that in any vector space, x equals 1.x. So x plus y is equal to 1.x plus y. Since both x and y are in W by assumption, the sum of x and y again is in W. And to conclude, I need to show that W is closed under scalar multiplication. I give myself an arbitrary scalar lambda and an arbitrary element x of W, and I want to rewrite lambda x again in the form of that highlighted blue box in our theorem. And it's easy to do now because we can write lambda x as lambda x plus 0. X is in W by assumption, and we have shown that 0 must also be in W. Therefore, lambda x plus 0 is in W by our assumption on the set W. We have thus shown that W is closed under addition, scalar multiplication, and contains the 0 vector. It is thus a subspace of V. Let's elucidate what subspaces actually are. Informally, subspaces of a vector space V are those subsets of V on which the operations of V induce a vector space structure. Let's be a bit more formal. If W is a subspace of a vector space V over a field K, then W is a vector space over the same field K in its own right for the induced operations from V. By the induced operations, what I mean is the following. If I take a pair of vectors in W, I can add them up in V, but because W is a subspace, I can conclude that the sum of these two vectors is again in W. Thus, I have defined an operation on W cross W valued in W that I still call the addition by restricting the domain and the codomain of the addition of V to W. Similarly, I can define a scalar multiplication. If I take a vector of W and a scalar, I can multiply them in V using the scalar multiplication there. But by definition of W being a subspace, the product of a scalar by a vector of W is again a vector of W, and thus I have defined a map from K times W to W. I have two binary operations on W that are well defined and have the right signature so that I can ask, is W itself actually a vector space for these operations? To prove that, I would have technically to go through the entire definition of a vector space. We remember it's quite long. I'd have to prove that W with the addition is an abelian group, distributivity of the scalar multiplication with respect to the addition, and a few, 3 specifically, compatibility conditions. But most of those properties are obvious. Every time you have a quantifier of the form for all that applies to a bunch of vectors in V, well, it's still the property listed after is still true, if it was true in V, when you restrict to your for all to a bunch of vectors in W. So really, there is actually one key thing to check in the proof that is interesting. But let's start to see where it is. So I'm going to start the proof that W with the addition is actually a group. First thing you note is that 0 is in W by assumption of W being a subspace. Then you note that the addition is associative on W, as I just said, because we restrict the addition to W. It's easy to check associativity holds simply because it does hold in V. But now I have an interesting problem. We want to prove that if we take an element of W, its additive inverse, minus x, is also an element of W. If W was just a group, not a vector space, I would have to add some conditions for this to be true, and to discuss the notion of subgroup. But here, because we have vector spaces, we can use the external multiplication. So if x is in W, then W being a subspace, minus 1 times x is again in W. Yet, with the work we have done in previous lectures, minus 1 times x equals to minus x, the additive inverse of x. So indeed, every element of W has an opposite for the addition because, well, minus x is still an opposite of x, whether it's in V or W. It's unique anyway. And so we have proved that W is indeed a group for the addition. We'd have to prove it's an abelian group and the other properties, but that, as I said, follow trivially from the properties of V. So indeed, W with these two restricted operations is to induced operations is a vector space over the same field K in its own right. If you think about it, the converse of that statement is almost self-evident. It's not even quite clear what we would mean by this. That is, suppose I take a subset of a vector space V, and I want to say that, well, that subset is a vector space for the induced operations from V. Well, the problem here is, what does induced operations mean? If you look at the proof here, what I mean is, if I took two elements of my subset and I add them up, I would have to get an element of that subset again. Otherwise, I don't have an addition from the set to itself. I have an addition from a set to some larger set. It doesn't fit the signature of a vector space. Same with the scalar multiplication. So any set that pretends to be a vector space inside of a larger vector space must be closed under addition and scalar multiplication. And on top of it, since you're a vector space, you must contain a 0, but 0 being the neutral element for addition, it has to be unique. So it's very easy to see that if I'm a vector space inside of a larger space for the induced operations, the only way it even makes sense to say that, let alone, to discuss it, just to make sense of that statement, I'm already a subspace automatically. So the converse is trivial. It's just a matter of simply making sense of what it would even mean. So now we have an understanding of why we introduce subspaces. They are simply a special kind of vector spaces that happen to be defined using a larger vector space. I am going to give you a few exercises, namely 4 subsets of R3, and I would like to know which of those subsets are subspaces, which are not, and of course prove your answer, your guess. I'm going to give you a little while. I suggest you pause the video. I will solve those problems on the next slide. Let's go over these first examples. W1 is defined as a sort of parametrized subspace. For any two x and y in R², we define an element of R³ as written here. The first thing we observe is that 0 actually belongs to W1. This is simply observed by setting x equals y equals 0 in this parametrization of our space. And then I'm going to use the characterization behind, so already omega1 is not empty, W1 is not empty, and I should say very often you will prove that a particular candidate for being a subspace contains a 0 vector. That's how you'll show that they're not empty. It's a pretty typical pattern. But now I want to prove that if I take any two arbitrary vectors in W1 and an arbitrary scalar lambda, then indeed lambda times W1 plus W2 will again be inside the big space, the set W1. That will, by the characterization in the previous slide, allow me to conclude that indeed W1 is a subspace of R3. All right, so what does it mean to be an element of W1? It means that you can be written in a particular form. In other words, there exist xy and y1 such that W1 is indeed equal to 2x1, 3y1 minus x1, x1 plus y1. I just read here what the set W1 is consists of, and similarly for the element W2. Then I simply compute lambda of omega1 W1 plus W2. The computation is on the slide. I'm not going to read every letter. It's probably easier to just read it. What's important is that once you group the terms appropriately, you see that lambda omega1 plus omega2 is of the form 2u 3v minus uu plus v. It's the same form as what I need to conclude that this combination of vectors is indeed in W1. I just have to have the right u and the right v. I wrote them for you on the slide. So I was able to express lambda W1 plus W2 as yet another element of the set W1. Since W1 is also containing 0, my characterization allows me to state that W1 is indeed a subspace of R3. So let's look at another example. Looks like this W2 set. Now, this W2 set is a little bit different. What happens here is you could, for instance, ask yourself if 0 is in W2. It's usually, as I said, the way you go to prove that a subset is not empty, you want to usually get the 0 in there. There might be situations which are different, but that's sort of the typical approach. But here, if I try to find whether 0 belongs to this W2 set, I have to solve a system of equations. Only two equations that matter here. We have x equals 0 and x equals 1/2 at the same time. Well, this has no solution, so there is really no way to get the 0 vector of R cube inside of W2. And right there you can stop. By definition of a subspace of R cube, we should have the 0 vector in it. We don't, so W2 is not a subspace. Here's another example that will fail to be a subspace, but for a different reason. So W3 is this set composed, of a graph of a function in 3D space. We do observe that 0 is in fact in that W3. This is not important for my proof. I just want to point that out to you, that the reason why W3 will fail to be a subspace is different from the reason W2 failed to be a subspace. 0 is in there. However, I can find two vectors in W3, namely 1, 1, 1, which is obtained by setting x equals 1 in the equation parametrizing W3, and another vector, 2, 4, 2, setting x equals 2, whose sum, which is 3, 5, 3, is actually not an element of W3. If the first coordinate is 3, the second coordinate has no choice and must be 9. Well, here it's 5. So W3 is not a subspace of R squared. It is not closed under addition. So some spaces are not subspaces. As you can see, of course, it is a heuristic statement, but it's worth noting that typically, if something nonlinear shows up in the definition of a space, of your set, I should say, you have possible reasons to believe that maybe it won't be a subspace. And to, of course, disprove that a particular set is a subspace, you want to find a counterexample to one of the fundamental properties that one of the properties of the set of being a subspace does not hold. Let's look at our fourth problem here. This is a little bit different. The first problem, W1, which was a subspace, was given by parametrizing vectors in R cube in a sort of linear way using two variables in R squared. Well, two variables in R, one variable in R squared. W4, on the other hand, is a different kind of set. We have a set of x, y, z's in R cube satisfying a linear equation. And, well, again, we note immediately that 0, 0, 0 is in particular a solution to this homogeneous linear equation. And then if we take two elements of W4, that is two solutions to that equation, and an arbitrary scalar, then after calculating what lambda times the first solution plus the second equals 2, we can plug in our equation and check, by simply grouping the terms in an obvious manner, that again, lambda times the first solution plus the second solution is again a solution to that linear homogeneous equation. Therefore, we have shown that W4 is indeed having the property of the characterization of a subspace. It is itself a subspace. It's not empty. It contains 0. So W1 and W4 are actually very particular spaces, but in fact, I should say in some fundamental sense, that's basically all the spaces of this form in R3. 1 was really the image of a linear map, the range of a linear map, while this one on the screen right now is the pre-image of a linear map. The linear map would be the map that to three numbers, x, y, and z map, the value 3x plus 2y minus z. It goes from R cube to R. It's clearly linear. And W4 is a pre-image of the singleton 0, which is a subspace of R. And so we have sort of a connection between linear maps and subspaces, which we will return to on the next slide. Let me give you a list of other examples of spaces of functions that are subspaces before we move to connecting linear maps and subspaces. First, the set of all polynomials function over R, you can prove that's a subspace of the set of all functions from R to R. The operations here are pointwise addition and pointwise scalar multiplication. In the same vein, the set of continuous functions from your favorite topological space to R is a subspace of the vector space of all functions from X to R. So X could be any topological space that you want. The simplest example maybe could be something like X equals the closed interval 0, 1, or something like that. There are, of course, many such spaces. The set of 2 pi periodic functions from R to R is a subspace, again, of the set of all functions from R to R. All of that is easy. All you have to do is, in all these examples, of course, the 0 function is in there. And on top of it, you take 2 functions, for instance, 2 pi periodic functions from R to R of an arbitrary real number lambda. Well, if you calculate lambda times the first function plus the second, it's easy to check it's still 2 pi periodic. So here you go. It's a subspace. The proof is as easy as that. The proof for the second example involves knowledge of continuity, but from your calculus class, for instance, for function from R to R, you know that the sum of continuous function is continuous. Multiplying a continuous function by a constant still makes it continuous, and of course the 0 function is continuous. So all these examples are reasonably easy. Here's another little example. I take A strictly less than B, and I look at the set of functions that satisfies the mean value theorem. So they look like this. That satisfies the assumption, if you want, of the mean value theorem. There are continuous functions on the closed interval AB, valued in R, which are differentiable on the open interval AB. And that is a subspace of example 2. I mean, you can see that all the elements of this space empty of AB are in particular continuous function on the closed interval AB by assumption. So that's exactly example 2. And inside there, added another linear condition, which is simply the function are differentiable. And as you well know, if you have 2 functions f and g and some real number lambda, then if f and g are differentiable on the open interval AB, lambda times f plus g is also differentiable on the interval AB open. So here you go. Again, the 0 function is in there. It's very simple. It's an example of a subspace. And here's another funny subspace. Again, I take something from example 2. I take a subset of example 2, a set of functions that are continuous on the interval 0, 1, such that some linear function applied to that function is 0, namely the integral from 0 to 1 of f of t sine of 2 pi t dt 0. You can check that, in fact, this is, again, the set that is a pre-image of a singleton 0 by a linear function. And the linear function here is the function that to any continuous f maps its integral between 0 and 1 times, well, the integral between 0 and 1 of that function f times sine of 2 pi dot. That's a subspace. And the argument is the same, but rather than for many of this example, in fact, example 3 and example 5, and to some degree example 4 as well, can all be seen as special cases of the next slide, where linear functions indeed provide us with many examples of subspaces. So there are many subspaces. We have suddenly an extremely rich collection of new spaces, new subspaces, at our disposal. So if you take V and W, 2 K-vector space, the first thing I'm going to prove, which is in the sort of flavor of the previous slide, is that the set of all linear maps from V to W is itself a subspace of the set of all functions from V to W. Now, the function from V to that is such as 0 all the time, the constant function equals to 0 is obviously linear, and it's a 0 vector by construction of the space of functions from V to W. So we have that this homomorphism space, the space of linear maps, is indeed not empty, it contains a 0 vector. And using my characterization, what I must do is take 2 linear functions from V to W and an arbitrary scalar lambda. I'm going to call this 2 linear function phi and psi, and I want to show that lambda phi plus psi is again linear from V to W. But as it were, we also have a characterization for linearity, so we take any 2 vectors x and y in V, and some scalar mu in K, and I calculate lambda phi plus psi. That's a function I want to prove is linear. Okay. And I apply to mu x plus y. All right. So, well, to calculate this, I expand. So first, what is a function lambda phi plus y? By definition, it is calculated as on the slide here. That's the definition of what addition of functions mean and scalar multiplication of function mean in the space of functions. Then I use the fact that phi is linear and psi are linear to expand this expression as such. Then I group my terms a little bit. Basically, I group my terms based on their arguments inside the function. And then you recognize by definition again that indeed we have proven that lambda phi plus psi applied to mu x plus y is mu times this function, lambda phi plus psi, applied at x, plus this function, lambda phi plus psi, applied at y. That is a characterization of linearity. So I have proven that lambda phi plus psi is indeed a linear function from v to w. This is enough to conclude the theorem indeed holds. This is very interesting. We have an interesting category on our hand here. If I give you two vector spaces, then the collection of homomorphisms from one to the other is again a vector space. It is a subspace of a larger vector space. And that is quite remarkable because now, of course, we can sort of continue with this construction. We can look at homomorphisms from the set of homomorphisms of a vector space to another, the whole thing to yet another vector. So you can see how we can build now many examples of vector spaces. This will be a very important topic for us later. There are other connections between linear maps and subspaces, and those, as I announced a little earlier, explain many of the examples we have encountered. This is an important theorem. It says that if you have a linear map between two vector spaces v and w, let's call this linear map phi, then the preimage by phi of any subspace of w is again a subspace of v, whereas the image by phi of any subspace of v is again a subspace of w. So the short of it is, morphisms, that is linear maps here, preserve subspaces, either by pulling them back or pushing them forward. Let's prove this theorem. I'm going to start with the first bullet point here. So I take two vectors in the preimage of G, where G is some subspace of W. And I take an arbitrary scalar lambda. I want to prove that lambda W plus Z is still in the preimage of G by phi. That is my characterization. That, and of course, the fact the preimage should not be empty. But to prove that lambda W plus Z is indeed in the preimage of G by phi means that if I apply phi to lambda W plus Z, I should get an element of G. That's what being in the preimage means. So I'm calculating phi of lambda W plus Z. It's lambda phi of W plus phi of Z that is owing to the linearity of phi, which is assumed. And because G is a subspace, you recognize that I know that phi of W is in G and phi of Z is in G. I know that because W and Z were in the preimage of G by phi. Therefore, phi of W and phi of Z are in G. And therefore, you recognize by the characterization of subspaces that this element again is in G. And therefore, lambda W plus Z is the preimage of G by the map phi. Well, I need to make sure that this preimage is not empty, but that is more or less immediate because linear maps map 0 to 0. So the first property we actually proved about linear maps. So in particular, phi of 0 is 0. 0 belongs to G since G is a subspace. Therefore, the 0v belongs to the preimage of G by phi. And so we have all we need to conclude that the preimage of G by phi is a subspace of V. Now, let's look at the other bullet point here. The push forward of a subspace of V by phi must also be a subspace. So the principle is similar. I'm going to take two vectors in the image of f by phi. F is the subspace of V. And I'm going to take an arbitrary scalar lambda. So what does it mean to be in the image of f by phi? It means that I can find for two vectors, x and y and f, that w is phi of x and z is phi of y. That's just what it means to be in the image of f by this map. Now, phi is linear and f is a subspace. So the first thing actually that is important here is f is a subspace. So lambda x plus y is in f since x and y are in f. and as characterization of our subspace tells us, this is an element again of F. And this is where I use linearity. If I calculate lambda W plus Z, then simply replaces W and Z by what they are. It's lambda phi of X plus phi of Y, which is phi of lambda X plus Y. This is a linearity of phi right there. And since lambda X plus Y belongs to F, phi of lambda X plus Y belongs to the image of F by phi. Again, 0 is phi of 0. So 0 is in the image of F by phi, and therefore phi of F, as announced, is a subspace of W. This, again, is a very powerful way to construct examples. You could return to the examples at the beginning of this lecture, W1 and W4 they were called, and check that in fact both of them are examples of this theorem, application of this theorem for the right map and the right subspaces, covering actually both cases, both bullet points here. In fact, to be more specific, let's define some terminology here. If I have a linear map between two k-vector spaces V and W, the kernel of this map, sometimes called the null space, but I will use the terminology kernel. The kernel of this map, simply denoted by k of phi, is simply the pre-image by this map of the singleton 0. While the range, as we well know, is the push forward of the image of the entire space V. Well, a corollary of what we have proven on the previous slide is that for any linear map phi, both the kernel and the range are subspaces of the respective domain and codomain spaces. For instance, the kernel is a pre-image by a linear map, namely phi, of a singleton 0, and 0 is a subspace of W. It's very easy to check. I'll let you do that somewhere on your notes, but 0, the singleton 0 contains 0, and if I do lambda times 0 plus 0, I get 0. So this little tiny singleton is a subspace of W, and, well, its pre-images by the linear map phi is what I call the kernel. By the previous theorem, the pre-image of a subspace is again a subspace. Even easier in a sense for the range, you see V is a subspace of itself. Again, that is a trivial observation, but here is my occasion to mention it. V is obviously a subspace of itself, and therefore the range of phi, which is the push forward of V by a linear map, is again a subspace of W. So the kernel is very useful because we use it all the time to study whether a particular linear map is injective. And you have morphisms, but generally speaking functions, but morphisms in particular, when dealing with algebraic structures, whether they are surjective or injective is typically a big deal. So injectivity is synonym for one-to-one, and surjectivity is synonym for onto. In the case of linear maps, it turns out that there is a very nice and extremely useful characterization of injectivity. It says that a linear map phi from V to W, V and W two vector spaces, a linear map V from W is injective if and only if its kernel is reduced to the singleton 0. Now remember, 0 is a subspace of V, and it's really the smallest subspace we can have since the empty set cannot be a subspace. We must have the neutral element as an element of any space, vector space. So this is a sort of minimality condition on the kernel. The proof is fairly straightforward. If phi is injective, then the kernel, being the pre-image of a singleton, must be a singleton. Well, the function is one-to-one. So this follows immediately. There's no other vector in V that can map to 0, since we already know that phi of 0 is 0 and phi is injective. On the other hand, if the kernel of phi is the singleton 0, and if I take any two vectors in V, such that phi of x, any two vectors x and y in V, such that phi of x equals phi of y, so if phi takes the same value on these two vectors, then using the algebraic rules we worked on in our previous lessons, 0 is equal to phi of x minus phi of y, which is equal by linearity of phi to phi of x minus y. What that means is that phi of x minus y is 0, so x minus y is the kernel of phi. Now, in turn, what that means is that since the kernel of phi is reduced by assumption to the singleton 0, x minus y must be 0. That's all there is in there, which gives us the result that x must be equal to y. So for any two vectors x and y, if phi of x equals phi of y, then x equals y. That's the definition of injectivity. I'll make a remark, it's not a proof or a theorem, it's just a definition. By definition, of course, what it means to be surjective for any function is simply that the image of the domain is the entire codomain. So here, by definition, a linear map is surjective if and only if its range is its entire codomain. But it does, I just indicated because, well, in the previous slide we talked about the range and the kernel as sort of these two spaces naturally associated with a linear map. Both of them do characterize a fundamental property of the map. Let's conclude this section with a transition to our next lecture. What else can I do with subspaces? We now have many potential examples of subspaces, but it turns out that what is fascinating in linear algebra is that the set of subspaces is a collection of all the subspaces of a given vector space, like all the subspaces of our cube, or all the subspaces of the functions from the continuous function on 0, 1, or any of those. This collection of subspaces have many very remarkable properties. First of these properties that I will discuss here is that, for instance, I can add subspaces to get a new subspace. Now let's understand this a little bit. If I give you two subspaces of a vector space V, let's call them W1 and W2, then in general the union may not be a subspace. And here's a counterexample. I mean, to put it in geometric terms, you look at the x-axis and the y-axis of our square. Those are indeed subspaces. You can check that very quickly, but their union is not, because I have a vector that I can write as a sum of two vectors in the union of W1 and W2, yet it itself is not in the union. So I fail to be a subspace. You can check this counterexample. But if I want a subspace, and we'll discuss later that in fact this is the smallest you can get in a precise sense, but for now, a good replacement to the union, something larger that will be a subspace, is what's called a sum. So if I take two subspaces of V, then I'm going to define W1, two subspaces W1 and W2. I'm going to define W1 plus W2 as a set of, well, all possible sums with one term in W1 and one term in W2. Just add them up, all of them. And well, this sum is always going to be a subspace which contains the union. So this is sort of the candidate we have for replacing, if you want, the union of subspaces, since that is not a subspace in general. Okay? So I'm going to, again, ask you to pause the video and try to prove the theorem for yourself, and I will give you the answer on the next slide. So here's a proof. Again, we wish to apply the characterization of subspaces. It's always the same trick here. So I want to prove that 0 is in my intersection, my sum, I apologize, my sum of two vector spaces. Now, well, I just want to prove that the sum is not empty, but as I said, it's typically done by showing that 0 is in it. And of course, 0 is, well, 0 plus 0, which is interesting here simply because 0 belongs to both W1 and W2. So I was able to express 0 as a sum of something in W1 and something in W2. So here you go, 0 is in there. And then I'm going to take two arbitrary vectors in the sum. So what does that mean when you take two elements, x and y, in W1 plus W2? Well, you go back to the definition highlighted in the theorem. It means that, say, x is the sum of a vector W1 and a vector W2, with W1 in the big W1 and little W2 in big W2. And again, y is also a sum of two vectors, one in W1 and one in W2. Then I take an arbitrary scalar lambda, and I want to show that lambda x plus y is also in the sum of the space W1 and the space W2. So to do that, well, I calculate my expression by using the fact that x is a sum and y is also a sum. Then again, we use all these algebraic properties. We know we can recombine here. Really, I'm actually just using commutativity and associativity of the addition. And I'm also using, the distributivity of the external multiplication. Those are the property I'm using. But whatever they are, you see that I'm able to write the sum of x, the lambda x plus y, as a sum of the first vector, lambda w1 plus v1 in the notation of this proof. And if you look where w1 lives, well, it lives in the subspace w1. And if you look at where v1 lives, it also lives in the subspace w1. And therefore, lambda w1 plus v1 is again inside w1 because w1 is assumed to be a subspace. The same for the other term, it belongs to w2. So I've written my combination lambda x plus y indeed as a sum of something in w1 and something in w2. So I can conclude that w1 plus w2 is a subspace. Now, on top of it, the union w1 and union w2 lives inside this sum. It's a fairly simple observation. If you take any vector, say in w1, let's call it v1, then this vector v1 is equal to itself plus 0. And since 0 is in w2, I've been able to express v1 as a sum of something in w1 and something in w2. So it is in the sum of those spaces. And that gives me that the whole subspace w1 lives inside the sum w1 plus w2. The same is true for w2. So if you put that all together, it says that if you look at the collection of subspaces of a vector space, it's not closed under union, but it is closed under sort of a replacement for union called the sum. Okay. Well, another relevant theoretic operation would be the intersection of subspaces. We could ask, is the intersection of subspaces in general a subspace? And then the other main set theoretic operation is complement. But it's immediately clear that complementing in the naive sense a subspace doesn't give you a subspace, because after all, if I take the complement of a subspace, that complement cannot contain 0. So there's no hope. We will see that in fact there are notions that can be used to replace, so to speak, the complement, but they can be quite complicated in general, though in the realm of this class, infinite dimension, things will work well. But for intersection, well, we will start our next lecture on this topic, because it turns out that it is very important, and I don't want to spoil the fun, so I invite you instead to go and watch lecture number 5, which will be about linear span.